Good morning everyone. Today we are going to discuss about some important results regarding electrostatics of conductors. So the first point is, which you already know, that inside a conductor electrostatic field is zero. Now we already know it for charged cell, charged spherical cell. Now to understand it, let us consider a conductor which may be charged or neutral, or also there is maybe some external electric field. And you already know that the conductors contains free electrons which move randomly, but there is, in static situation, there is no current. There is no current inside or on the surface of the conductor. But if there was some electric field, due to the electric field the charge would experience some force and they would start moving against the direction of the, as the electrons are negative, they would start moving in the direction opposite to the electric field. But that we don't see that there is no movement of such, there is no such movement of charges inside. Also, if we apply some electric field from outside, the charge would distribute themselves in such a way that inside it there is no electric field. They would just distribute them. We'll know it properly when you study polarization after some time. Now second point is, at the surface of a charged conductor, electric field must be normal to the surface at every point. Now to understand this, let us consider any conductor of any shape. Okay, suppose it has some charges and due to which it produces some electric field. And if the electric field, say at this point, is not perpendicular at this point to the surface, say along in this direction, instead of perpendicular, this is the actual direction, but now to understand it, suppose the direction of electric field is in this direction. So in this case it has some component along the surface, but in this case actually you have to take the point exactly here. So in this case it will not have any component towards the surface. So if the electric field is like in this direction, then it would have some component along the surface. So the actually charges on the surface would feel some force and they would start moving. But that is not the case, they don't move. So the electric field is actually perpendicular at every point on the surface. Now next important thing is that the interior of a conductor does not have any excess charge in static situation. So you know that generally any material is electrically neutral. Now suppose you take any conductor and give it some charge. Okay, so according to this, the charge will only reside on the surface, because we already know that no matter it is whether charged or uncharged or there is any external electric field, the electric field inside the conductor should be zero. Now if you take any small Gaussian surface, okay, the electric field is zero inside it, so there should not be any flux. So since E equals to 0, phi should be 0. You can take anywhere, any closed curve, so phi should be 0. So if phi should be 0, the charge enclosed by it should be also be 0. So inside the conductor there cannot be any excess charges. Okay, whatever charge you give it to it, they will reside only on the surface. Number 4 is, the electric potential is constant throughout the volume of the conductor and has the same value as on its surface. So if you have a conductor, the value of potential at surface or at inside or wherever, you can take any point, the value of potential will be constant at every point of the conductor. Now we already know that inside the conductor E equals to 0, and again we know that at the surface the electric field is perpendicular at that point of the surface. So you see, inside, since the electric field is zero, the charge will not feel any force, so the work done is zero. Again here, the electric field is perpendicular, so if you move on the surface, you are moving perpendicular to the force, so in that case also the work done is zero. So anywhere you take any charge from any point to anywhere, the work done is zero. That means the potential is constant throughout. So inside or outside, the potential is same. So now if you consider any sphere, now we know the electric field at any distance due to this is equals to 1 by 4 pi epsilon naught q by r square if the sphere has charge q and the distance is r. If you want to find the potential at this point, and the electric field on the surface is, just if the radius is r, just change r to capital R at surface. So if you want to find the potential with respect to the electric field, we already know E equals to minus dV dr or dl or ds. So if you just put the value and integrate it, you will get V equals to 1 by 4 pi epsilon naught q by r. So at the surface, you will get 4 pi epsilon naught q by r. So this is the electric field on the surface, but inside it the electric field is zero. Potential on the surface, this one, and also inside, this is the same. So if you want to draw a graph how the electric field and the electric potential varies, so this is say E with distance for sphere. Say the radius of the sphere is r. So the electric field inside 0. So up to small r equals to r, no electric field. At the surface, this is the value. So at surface, this is the value like this. Then it goes on decreasing with square of r. So it will be like this. And if you want to draw potential versus distance graph, from center to the surface, the potential is same. So if this is r equals to r, from center to surface, this is same up to this point. Then it will decrease as 1 by r, not so rapidly, but it will decrease like this. So this is how the electrostatic field and electrostatic potential varies for a sphere. Now next is electric field at the surface of a charged conductor is sigma by epsilon naught to n cap, where n cap is the outward normal at the point, at any point on the surface. Now to prove it, consider any shape of conductor, and suppose we want to find the electric field on the surface. Now to find that out, we'll consider a small cylinder as Gaussian surface. Okay, this cylinder is very short, and this point is actually lies very close to the surface of the conductor. Now the electric field is radially outward. Now we will apply Gauss's law. So again here there are three surfaces, this one, and this curved one. For curved one, S vector and neither mutually perpendicular, so there will be no flux through it. Now for this, where inside the conductor the electric field is zero, so we do not have to consider any part inside the conductor. So we are left with only one surface, this one. So for that we can write E dot ds equals to q by epsilon naught. Now here q is the charge enclosed by this Gaussian surface. Now if the surface charge density of this curve of this conductor is sigma, and this area say is ds, so you can write q as sigma ds. by epsilon naught. So E dot ds both are in the same direction. So E ds equals to sigma ds by epsilon naught, or E equals to sigma by epsilon naught. If we write in vector form, E equals to. Now we can easily find the electric field at the surface of the sphere using this. Suppose the sphere has a charge q, so the surface charge density will be automatically q by 4 pi r square. This is for sphere. So electric field will be sigma by epsilon naught. Just put the value 1 by 4 by epsilon naught q by r square. This is the electric field on the surface. We can find from this equation as well. So these are some of the important points about electrostatics of conductor. Now let us discuss about dielectrics and polarization. Now dielectrics are basically insulators, but there is little difference. Okay, the difference is when you put an insulator in an external electric field, they gets polarized. Now what is polarization or how they get polarized, we will discuss a little later. Now first consider, we put any conductor in an external electric field. Okay, suppose we have a cylindrical conductor, for example, and we put it in an external electric field, say E naught. Now the conductor has a lot of free electrons. So as soon as we put in an external electric field, the electrons will get attracted and they will start accumulating on that surface. Okay, so there will be negative charge and there will be lack of negative charge, so this will appear as positive. So actually inside the conductor, the electrons will be affected because of the external electric field. Now since there are negatively charged, accumulation of negatively charged, and it is positively charged, there will also be an electric field inside, which is exactly opposite direction to the external electric field. So now as long as this external electric field is greater than the internal electric field, there will be more accumulation of charges. Now with more accumulation of charges, the internal electric field will increase. Okay, so as it goes on increasing, after a certain time the external and the internal electric field becomes equal and opposite. So since the electric field cancels out each other, so inside the conductor the electrons will not feel any forces, so the accumulation of charge will stop. So this is how in the inside the electric field actually becomes zero in a conductor. But if we take any dielectric, we see that in the inside the electric field reduces, but it does not become zero like a conductor. So there are actually two types of dielectrics. One is non-polar and the other one is polar. The example of non-polar molecules are H2, CO2, etc. and polar is HCl, H2O. Now we have to find out what is polar and non-polar actually means. The polar and non-polar means, in case of a non-polar molecule, the center of positive and negative charge actually coincides. There is actually no separation between the center of positive and negative charges. But in case of polar molecules, there is actually some separation. Okay, for example, HCl, you already know that H is plus Cl minus. This is how they get connected. So from negative to positive, say this is Cl and this is H. This is slightly plus, this is minus. So there is a separation between positive and negative. So there is a dipole moment in this direction. Now let us find out how they behave in an external electric field. Now first consider nonpolar molecules. In general, suppose you have a nonpolar molecule substance. So here we just draw it little bit differently. So positive and negative are actually coincide, giving no dipole moment. Here E equals to 0, there is no external electric field. Now once we put it in an external electric field, say in this direction E, the charges actually get separated by a very small distance. So they actually becomes like this. Like this. So actually, with the introduction of a net external electric field, so we see some dipole moment developed. Okay, this is called polarization, and we measure it as the net dipole moment developed per unit volume. Now it is very obvious that the more the magnitude of the electric field, the degree of polarization will be more. But in case of polar molecules, the charges are already separated, but they are randomly oriented because of the thermal energy. So suppose someone is like this, next one is like this, some like this. So they are randomly oriented. As a result, the net dipole moment is 0. Now once you put it in an external magnetic field, you already know the dipoles will try to align itself along the electric field. So this is for electric field equals to 0. Now for a net electric field, they will not exactly align everyone, but if you increase the electric field, after certain time all the dipole will be aligned along the electric field. So now there will be some dipole moment, non-zero dipole moment, and since P is directly proportional to E, the more the value of electric field, there will be more polarization. Actually this is dipole moment, and the polarization is denoted as capital P, which is proportional to E, and this is dipole moment developed per unit volume. P is P. So the dielectrics actually get polarized when we placed in an external electric field. Generally insulators do not get polarized. Now what happens if you keep on increasing the electric field? If you keep on increasing the electric field, there is a breakdown happens. That means the dielectric behaves like conductor. Though its conductivity will be very less, but it will behave as a conductor. So the maximum electric field that any dielectric can withstand, that means it does not go to its breakdown region, that electric field is known as dielectric state. So this is all about dielectric and polarization. Tomorrow we will discuss about capacitors.